What if you could make any amount of money with the fewest coins possible, no matter how weird the denominations? CoinChange is a Pattern Mastery 100 legend and a favorite at Apple, Facebook, Microsoft, Salesforce, and Amazon interviews. This dynamic programming classic tests not just your DP chops, but your ability to break a tough problem into smaller, reusable subproblems. Let's crack the pattern that unlocks hundreds of interview questions. Let's break it down. You're given a set of coin denominations and an amount. Return the minimum number of coins needed to make that amount. If you can't make it, return -1. You can use as many coins of each denomination as you want. Now let's assess our approach. Brute force would try all combinations, exponential time. Instead, this is a perfect fit for dynamic programming. For every amount from 1 to the target, we'll keep track of the minimum coins needed. At each step, we look back at the best answer for current amount, each coin. This bottom-up DP builds the answer efficiently, and we only need a simple array. Here's the plan. Create a DP array of size, filled with amount +1, a value bigger than possible. Set DP0 equals 0, 0 coins to make amount 0. For each amount from 1 to the target. For each coin, if coin less than or equal to current amount. DP amount equals min DP amount coin +1. If DP amount is still amount +1, return -1, else, return DP amount. Let's try to implement it using solution 1. We begin by defining a class called solution. This is just the container where our dynamic programming method for the coin change problem will live. Here we define the method CoinChange. It receives an array of coin denominations and a target amount, and it returns the fewest number of coins needed to make up that amount, or -1 if it's impossible. We create a dynamic programming array called DP with amount +1 positions. Each DPA will eventually represent the minimum number of coins needed to make the value A. We fill the entire DP array with integer.max_value, which we use to mean unreachable or not yet computed. This sets a baseline that any valid solution will be smaller than. We explicitly set DP0 equals 0 because the number of coins needed to make amount 0 is 0, no coins required. This starts a loop from 1 up to our target amount. At each step, we try to figure out the best number of coins needed to make value A. This outer loop runs amount times, giving us a time complexity component of O amount. For each amount A, we loop through every coin in the coins array. This inner loop checks whether we can use coin C to help build the amount A. Combining both loops, the total time complexity becomes O(n) times m. This condition checks two things. A, C greater than equals 0. We can only use coin C if subtracting it doesn't make the amount negative. DPA, C, equals integer.max_value. The amount A, C must already be reachable, meaning, we already know how many coins it takes to make the remaining amount. If the previous condition is true, it means we can form amount A by first forming amount A, C and then adding 1 coin of value C. So we update DPA to the minimum between its current value and the value DPA, C, +1, the number of coins needed if we use coin C. This gradually builds the optimal solution for each amount. Finally, after filling the entire DP array, we check. If DP amount is still integer.max_value, then the amount is impossible to form, so we return -1. Otherwise, we return the computed minimum number of coins. And that's how this algorithm works. It first sets up a dynamic programming array, initializes unreachable values, then builds up solutions for every amount from 1 to the target by checking all coin combinations. Solution 1. Test case 1. Let's test our function using this input. Coins equals 1, 2, 5, and amount equals 11. The coins array represents the denominations available, and amount is the total value we want to build using the fewest number of coins possible. To make 11 using denominations 1, 2, and 5, the optimal choice is use 5, use another 5, then use 1. That totals exactly 11, and it uses 3 coins, which is the minimum possible. Our dynamic programming array builds solutions from the bottom up. DP0 equals 0 because no coins are needed to make 0. Each DPA stores the fewest coins needed for amount A. Once the table reaches DP11, it correctly identifies that the best solution uses 3 coins. And that's exactly what our program outputs, 3. And the expected result also matches, 3, confirming that the dynamic programming logic found the optimal solution. So, our implementation is correct. The algorithm successfully computes the minimum number of coins using a clean bottom-up DP approach, efficient and accurate. Now let's try another implement approach using solution 2. We start by defining the solution class. This is the container that will hold our recursive, memoized approach for solving the coin change problem. Here we create a memo map. This map remembers results we've already computed. For a remaining amount rem, it stores the minimum number of coins needed. Think of it like a notebook where we write down answers to subproblems so we don't solve the same thing again and again. This is our main method coin change. It receives an array of coin denominations and a target amount, and returns the minimum number of coins needed to make that amount, or -1 if it's impossible. Here we call a helper method DFS, depth first search, with the full amount. DFS will try all possible ways to build that amount by subtracting coins, and return the minimum number of coins needed. Once we get the result R from DFS, we check. If R is integer.max_value, that means no combination of coins could form the amount, so we return -1. Otherwise, R is a valid minimum number of coins, and we return it directly. Now we define the helper method DFS. It takes the coins array and a value rem, the remaining amount we still need to form, and returns the minimum number of coins required for that remaining amount. This is our first base case. If the remaining amount is exactly 0, we don't need any more coins, so we return 0. Second base case. If rem becomes negative, it means we overshot the amount, we used too much value. In that case, this path is invalid, so we return integer.max_value as a special marker meaning impossible solution from here. Before doing any more work, we check our memo table. If we've already computed the answer for this remaining amount rem, we return it immediately. We initialize min with integer.max_value, representing the worst case. We haven't found any valid way yet. As we explore different coin choices, we'll try to shrink this value. This loop goes through each coin denomination C in coins. For each coin, we try using it once and see what happens if we subtract it from the remaining amount. Here we make a recursive call to DFS with a smaller remaining amount, rem, C. This represents the idea. Let's use coin C, and then see the minimum coins needed for what's left. Now we check if the recursive result R was valid. If R is not integer.max_value, it means there is a way to form rem, C. In that case, using coin C plus that solution gives us R plus 1 coins in total. We then update min to be the smallest number of coins found so far, across all coin choices. We store the result for this remaining amount rem in the memo table. Next time we see the same rem, we can return this value instantly instead of recomputing. Finally, we return min, the best, smallest number of coins needed to build rem from this point. And that's how this algorithm works. It first sets up a memo table and a recursive helper to explore all ways to make the amount, then uses depth first search with memoization to efficiently compute the minimum coins for each remaining value. Efficient, simple, and elegant. Solution 2. Test case 2. Let's test our function using this input. Coins equals 2, and amount equals 3. This means we only have one type of coin, a coin of value 2. And we want to know if we can make the total amount 3 using it. Here's why the solution works. The algorithm uses a recursive DFS approach that tries subtracting each coin from the remaining amount. With only the coin 2, the recursion checks. 3 to 2 equals 1 remaining amount becomes 1. Then it checks 1 to 2 equals -1 invalid. We return integer.max_value. Every path fails because you simply cannot build 3 using only coins of value 2. The memoization map stores these failed results so they aren't recomputed repeatedly. And that's exactly what our program outputs, -1. And the expected result also matches, -1, confirming that our DFS plus memoization logic correctly identifies impossible cases. So, our implementation is correct. The algorithm successfully detects that there is no valid combination of coins to reach the target amount. Efficient, accurate, and reliable. Let's wrap up with a quick recap of the coin change problem, one of the most classic examples of dynamic programming in action. Breakdown recap. We began by understanding the task. Given different coin denominations and a target amount, we needed to find the fewest coins required to reach that amount, or decide it's impossible if no combination works. Assess recap. We compared potential strategies and realized that brute force recursion would try every combination, quickly becoming inefficient. Instead, we chose a bottom-up dynamic programming approach, where we build up solutions for smaller amounts and use them to solve larger ones efficiently. Structure recap. We structured our logic around a DP array, where each index represents the minimum number of coins needed for that specific amount. By iterating through all coin values and all subamounts, we continuously updated the array with the smallest count possible. Implement recap. After setting up the DP logic in LeetCode, our implementation ran smoothly, efficient, clean, and easy to follow. Check recap. We tested it using multiple inputs on LeetCode, confirming that the solution handled all cases correctly, including the ones where no valid combination exists. The key takeaway here is that dynamic programming shines when problems can be broken into overlapping subproblems. By building up from smaller results, we turn a seemingly complex challenge into a simple, systematic solution.